I'm going to be talking about angular velocity, angular frequency, and angular acceleration. Now, before I continue, let me finish drawing this XY coordinate system, and let me also draw a blue circle centered at the origin of that XY coordinate system. Okay, now assume an object is moving along that blue circle, okay, and assume that we want to denote the motion of the object along that blue circle. One way to do it is to give the functions x of t and y of t, right, where t represents time. And another way to do it is in polar coordinates. In polar coordinates, we would have r equal to a constant, and we would have theta of t, right? Okay, now in rectangular coordinates, we can define v sub x equal to the rate of change of x, and we could define v sub y equal to the rate of change of y. Okay, now likewise in polar coordinates we can define a variable equal to the rate of change of theta. Okay, that is referred to as the angular velocity, and that's denoted by the Greek letter omega. So let me write that definition down. So omega equals the angular velocity, which equals the rate of change of theta. Now I will be using radians per second for angular velocity units. Okay. Now if you wanted to use revolutions per second for some reason, you would be talking about angular frequency. Okay. Angular frequency is denoted by the letter f, the variable f, and if omega is given in radians per second, then omega over 2 pi is equal to the angular velocity. All right? I said that you're dealing with angular frequency if you're using revolutions per second. Okay? You can also refer to that as cycles per second. Now, in honor of a famous scientist by the name of Hertz, we denote angular frequency by Hertz. Okay? And that's abbreviated with a capital H and lowercase z. All right? So write those down. We're going to be using those two definitions. And let's now do an exercise. Suppose a car was driving along a circular racetrack and completing 1 revolution every minute. Okay? Let's calculate the angular velocity and angular frequency for that race car. So for 1 revolution, the change in theta is 2 pi radians. For 1 minute, the change in time is, well, it's 1 minute, which is also 60 seconds. So if I wanted to give the angular velocity in radians per second, it would be pi over 30 radians per second. I can divide that answer by 2 pi and get 1 over 60 hertz for the angular frequency. Okay? I hope you understand that. Now let's have you try to do an example. Okay, so assume a man is walking along a circular trail. A man walks along a circular trail. He traverses a quarter of the circle in 30 seconds. What is the angular velocity and angular frequency of the man? Okay, so pause the video and try to find angular velocity and angular frequency. Okay, I'll go ahead and do it as well. So for a quarter circle, the corresponding delta theta is pi over 2 radians. I'm going to divide that by 30 seconds, so I'm going to get pi over 60 radians per second. I hope that's what you got. And for the angular frequency, I'm going to divide that by 2 pi and get 1 over 120 hertz. All right. Let me now do some exercises involving graphs. So, what is the angular frequency of, the angular velocity that corresponds to the motion represented by the following theta versus time graph? Okay, so theta will be in units of radians, t will be in units of seconds, and let's say that a motion starts with a theta of 0 and a t value of 0 and continues until theta is equal to 10 radians and the time is equal to 5 seconds. All right, what is the corresponding angular velocity? All right, well, the angular velocity we know is the rate of change of theta. So for motion that corresponds to that graph, the change in theta is 10 minus 0, and the change in time is 5 minus 0, so I get 2 radians per second. Okay, notice that the angular velocity is equal to the slope of a theta versus time graph. That will help you to calculate angular velocities. Okay? Now, I'll keep that on the board, and I will, well, actually, no, let me clear the board. And I want you to calculate the angular velocity that corresponds to this theta versus time graph. Okay? So assume that an object was moving such that initially at time 0 it had theta equal to 7 radians, and then at t equals 4 seconds it had theta equal to 0 radians. Alright, so what is the angular velocity that corresponds to that motion? Pause the video and try to answer that now, please. Okay, I'll go ahead and calculate it now as well. So I'm going to focus on the horizontal and vertical intercepts to calculate the slope of the blue line. And I'm going to get negative 7 over 4. So negative 7 over 4 radians per second is the answer. And I hope that's what you got. All right, now let me switch gears and talk about something else. Now, the same way that we defined angular velocity equal to the rate of change of theta, we can define a variable equal to the rate of change of angular velocity. That's traditionally denoted by the Greek letter alpha. Okay, so alpha equals delta omega over delta t. So there's the definition of angular acceleration. And I'll be using units of radians per second squared for that. Okay? So now let's do an example calculation. So suppose that somebody walks up to a merry-go-round that's not moving and starts spinning it and gets it up to so that it's spinning at 5 revolutions per minute, and let's say it took the person 30 seconds to get it up to 5 revolutions per minute. Can we calculate the corresponding angular acceleration? Okay, so the initial angular velocity was 0 radians per second. The final angular velocity is, let's see, so 5 revolutions corresponds to 5 times 2 pi radians. 1 minute corresponds to 60 seconds. So 10 pi over 60 radians per second, pi over 6 radians per second. Okay, so now we can calculate alpha, which is the rate of change of angular velocity. So pi over 6 minus 0 over 30 minus 0. So pi over 180 radians per second squared. All right. Now, let me have you do an example. Suppose that somebody else walks up to a different merry-go-round that was initially stationary, and suppose that it takes the person 20 seconds to get the merry-go-round spinning with an angular velocity of 10 radians per second. So what is the corresponding angular acceleration for that process? All right, so go ahead and pause the video and calculate that now, please. Okay, so I'll go ahead and do it also. So the rate of change of omega is what I'm looking for. So 10 minus 0 because it was initially stationary. So I hope you got 0.5 radians per second squared for your answer. All right, and let me now do some examples involving graphical information. All right, so suppose that I had a changing angular velocity given by the following omega versus time graph. Give me a second to finish drawing it. Let's say initially at time 0 that is, let's say that the angular velocity was 0 radians per second, and let's say that 4 seconds later it was 20 radians per second. So what would be the corresponding angular acceleration? So angular acceleration is the rate of change of angular velocity. So for this example it would be 20 minus 0 over 4 minus 0, or 5 radians per second squared. Okay, now notice that angular acceleration is the slope of an omega versus time graph. Okay, now let's have you do an example involving graphical information. Would you please calculate the angular acceleration that corresponds to this omega versus time graph? So suppose that initially something was moving with an angular velocity of 5 radians per second, and then 10 seconds later the angular velocity was 8 radians per second. Okay? So let me, give me a second to just finish drawing the graph here. So 5 for the vertical intercept, and then I'll put an 8 there and a 10 there. Okay, so pause the video and calculate the corresponding angular acceleration, please. Okay, I'll go ahead and do that now. So you'll recall that the angular acceleration is the slope of an omega versus time graph. So for this example, the change in omega, 8 minus 5, is the rise, and the run is 10 minus 0, so 3 over 10, or 0.3 radians per second squared. Okay. By the way, let me also show you an alpha versus time graph. Okay, what would the alpha versus time graph look like that corresponds to the motion that I was just working with? Okay, let me draw a picture of that. So alpha was 0.3 and it was constant for 10 seconds. So for this motion, it would be a horizontal line segment. Okay, so there would be a graph that corresponds to that same motion. Okay, one last comment before I close. If you want a nice simulation that covers the information that I've discussed in this video, you might want to do an internet search for a simulation called PhET Ladybug Revolution. You might find that informative and useful. Okay?